The 2015 Uniform California Earthquake Rupture Forecast Version 3, or UCERF3, is the latest official earthquake rupture forecast for the state of California, superseding UCERF2. It provides authoritative estimates of the likelihood and severity of potentially damaging earthquake ruptures in the long and near term. Combining this with ground motion models produces estimates of the severity of ground shaking that can be expected during a given period, and of the threat to the built environment. This information is used to inform engineering design and building codes, planning for disaster, and evaluating whether earthquake insurance premiums are sufficient for the prospective losses. A variety of hazard metrics can be calculated with UCERF3. A typical metric is the likelihood of a magnitude M6.7 earthquake in the 30 years. Since 2014, UCERF3 was prepared by the Working Group on California Earthquake Probabilities, a collaboration between the United States Geological Survey, the California Geological Survey, and the Southern California Earthquake Center, with significant funding from the California Earthquake Authority. Highlights. A major achievement of UCERF3 is use of a new methodology that can model multifold ruptures such as have been observed in recent earthquakes. This allows seismicity to be distributed in a more realistic manner, which has corrected a problem with prior studies that over-predicted earthquakes of moderate size. The rate of earthquakes of magnitude 6.7 and greater is now believed to be about 1 in 6.3 years, instead of 1 in 4.8 years. On the other hand, earthquakes of magnitude 8 and larger are now expected about every 494 years. Otherwise, the overall expectations of seismicity are generally in line with earlier results. The fault model database has been revised and expanded to cover over 350 fault sections, up from about 200 for UCERF2, and new attributes added to better characterize the faults. Various technical improvements have also been made. Of the 6 main faults evaluated in previous studies, the southern San Andreas Fault remains the most likely to experience an M6.7 earthquake in the next 30 years. The largest increase in such likelihood is on the Calaveras Fault, where the mean value is now set at 25%. The old value of 8% is less than the minimum now expected. The previous underestimate is believed to be due mostly to not modeling multifold ruptures, which limited the size of many ruptures. The largest probability decrease is on the San Jacinto Fault, which went from 32% to 9%. Again, this is due to multifold rupturing, but here the effect is fewer earthquakes, but they are more likely to be bigger. Table B methodology. California earthquakes result from the Pacific Plate, heading approximately northwest, sliding past the North American continent. This requires accommodation of 34 to 48 millimeters of slippage per year, with some of that taken up in portions of the Basin and Range Province to the east of California. This slippage is accommodated by ruptures and aseismic creep on the various faults, with the frequency of ruptures dependent on how the slippage is distributed across the various faults. Modeling like its predecessor, UCERF3 determines this based on 4 layers of modeling. The fault models describe the physical geometry of the larger and more active faults. Deformation models determine the slip rates and related factors for each fault section, how much strain accumulates before a fault ruptures, and how much energy is then released. 4 deformation models are used, reflecting different approaches to handling earthquake dynamics. The earthquake rate model fits together all this data to estimate the long-term rate of rupturing. The probability model estimates how close each fault segment is to rupturing given how much stress has accumulated since its last rupture. The first 3 layers of modeling are used to determine the long-term, or time-independent, estimates of the magnitude, location, and frequency of potentially damaging earthquakes in California. The time-dependent model is based on the theory of elastic rebound, that after an earthquake releases tectonic stress there will be some time before sufficient stress accumulates to cause another earthquake. In theory, this should produce some regularity in the earthquakes on a given fault, and knowing the date of the last rupture is a clue to how soon the next one can be expected. In practice, this is not so clear, in part because slip rates vary, and also because fault segments influence each other. So a rupture on one segment triggers rupturing on adjacent segments. One of the achievements of UCERF3 is to better handle such multi-fault ruptures. The various alternatives, taken in different combinations, form a logic tree of 1440 branches for the time-independent model, and, when the 4 probability models are factored in, 5,760 branches for the time-dependent model. Each branch was evaluated and weighted according to its relative probability and importance. The UCERF3 results are an average of all these weighted alternatives. The grand inversion. In UCERF2 each fault was modeled separately, as if ruptures do not extend to other faults. This assumption of fault segmentation was suspected as the cause of UCERF2 predicting nearly twice as many earthquakes in the M6.5 to 7.0 range than actually observed, and is contrary to the multi-fault rupturing seen in many earthquakes. UCERF3 subdivides each fault section into subsections, then considers ruptures of multiple segments regardless of which parent fault they belong to. After removing those ruptures considered implausible, there are 253,706 possibilities to consider for FM3.1, and 305,709 for FM3.2. This compares to less than 8,000 ruptures considered in UCERF2, and reflects the high connectivity of California's fault system. A significant achievement of UCERF is development of system-level approach called the grand inversion. This uses a supercomputer to solve a system of linear equations that simultaneously satisfies multiple constraints such as known slip rates, etc. The result is a model that best fits the available data. In balancing these various factors, it also provides an estimate of how much seismicity is not accounted for in the fault model, possibly in faults not yet discovered. The amount of slip occurring on unidentified faults has been estimated at between 5 and about 20 mm year depending on the location and deformation model, with one model reaching 30 mm year just north of LA. Assessment. While UCERF3 represents a considerable improvement over UCERF2, and the best available science to date for estimating California's earthquake hazard, the authors caution that it remains an approximation of the natural system. There are a number of assumptions in the time-independent model. While the final model explicitly assumes elastic rebound dominates other known and suspected processes that are not included in the model. Quote, Among the known processes not included is spatiotemporal clustering. There are a number of sources of uncertainty, such as insufficient knowledge of fault geometry and slip rates, and there is considerable challenge in how to balance the various elements of the model to achieve the best fit with the available observations. For example, there is difficulty fitting paleoseismic data and slip rates on the southern San Andreas Fault, resulting in estimates of seismicity that run about 25% less than seen in the paleoseismic data. The data does fit if a certain constraint is relaxed, but this brings back the problem over predicting moderate events. An important result is that the generally accepted Gutenberg-Richter relationship is inconsistent with certain parts of the current UCERF3 model. The model implies that achieving GR consistency would require certain changes in seismological understanding that fall outside the current bounds of consensus-level acceptability. Whether the Gutenberg-Richter relation is inapplicable at the scale of individual faults, or some basis of the model is incorrect, will be equally profound scientifically, and quite consequential with respect to hazard.